Okay. So that is a thorough going over for the homework. Let's get on to the next business. Okay. So the next thing we're going to do is we're going to expand the sorts of problems that we can work on. So far we've talked about take a sample and get a mean, or take a sample and get a proportion. But another very common thing to do, or another very common thing you might be interested in when people are doing a study, is that you'd want to compare two different populations. For example, maybe we've talked about, say, average salaries. You might want to compare what's the average salary of men versus the average salary of women. For example, if you were a statistical consultant on a court case for gender discrimination, they'd say, hey, we want you to prepare a case that says that men are getting paid more than women. So you'd actually have to go do a study, and you wouldn't be saying, hey, what's the average salary in general? You'd say, what's the average salary of men versus the average salary for women, and you'd want to be able to compare those two things. So you'd take two separate samples and compare them. Notice that in this case, you really have two separate populations. What would the first population be? Men, and the second population is women. Okay. Right. So this approach is going to be slightly different because we really have two different populations. So the basic idea, a lot of the basics will be the same, but some of the specifics will be different. So let me go through some of the basic ideas. So first of all, let's talk about this in the context of making a hypothesis test. So in terms of hypothesis test, what could your claims be? Well, very similar. Yeah, exactly. One claim would be equals versus not equals, and what would another one be? Yeah, one would be greater than, and the other one would be less than. So again, this is the basic idea and the basic setup. Yes. Okay. So let's consider the case where we're comparing means using matched pairs, which the book also refers to as dependent samples. So first remember that we've got two different groups, and we're testing the outcome, or we're taking some measure for both groups. Now, what does matched pairs mean? You'll remember that from back in the semester. What does matched pairs sound like it means? Right. You take pairs and you match them together. And then in each pair, the first person is in group 1 and the second person is in group 2. So remember, the idea for this was that you want to make your sample for group 1 and your sample for group 2 as similar as possible. So the idea is that you go person by person and pair them up. The treatments are different, exactly. And so the idea is that the only thing that's different is the treatment. Exactly. Yeah, actually, this is Osher brought up a really good example from psychology. A lot of the time, psychologists, when they're doing a study, will recruit twins. Now, why would they want to recruit twins if they're doing a study?
They want to see if they'll put them in two different environments to see if they will still be the same.
Right. And exactly. because then you know genetically they're exactly the same. So genetics couldn't possibly have any impact on what the outcome is. Okay. Every subject, I should say, in each. Okay. So now the question is, how do you organize your data after the study? So let's go back to an example that we've talked about previously. Remember comparing the lifespan of people that drive a BMW versus that drive a Toyota. So that was an example that we talked about a while ago. And we said one way to do this was to take match pairs. For example, you take a 37-year-old man, or excuse me, take two 37-year-old men. One of them gets a BMW, one of them gets a Toyota. Then you take a pair of 25-year-old women. One of them gets a BMW, one of them gets a Toyota, etc., etc. You dig? Okay. So let's say, let me just throw the data at you, and then let's try to figure out what we would do, how we would analyze this data. So again, let's say, and this is the data actually from earlier in the semester. Oh no, I'm sorry, I'm just making this data up now. Let's say that the first pair is from the 37-year-old men. So the 37-year-old man that drove the BMW lived to be 81. The one that drove the Toyota lived to be 79. Okay. Then you got a pair of 25-year-old women. The one that drove the BMW lived to be 78. The one that drove the Toyota lived to be 82. Etc., etc. Now, how can we analyze this data? What do you mean the average for each pair? Yes. So one thing you can do is you can say all the BMW people live to be an average of whatever it is, and all the Toyota people live to be an average of whatever it is. And then you could try to compare those averages in some way. That's one thing you can do. But here's another thing that we can do. Remember that the first pair represents the pair of 37-year-old men. So can we compare the 81 and 79 directly?
Yes.
Absolutely. Okay. So when you compare 81 and 79 directly, what do you say?
That 37-year-old for the BMW
Live longer? Can we be more specific than live longer?
is longer than 37-year-old.
Well, right. Can we be more specific than just live longer? Live. Can we say how much longer? 2 years. Exactly. What about in the second pair? Right. 4 years. Right. But we've got to make sure that we keep our orientation correct. So remember what the claim. What was the? Do you remember this? Remember this question? What was the claim? Right. So the claim is that people with BMWs live longer. So for the first pair, it's 2 years longer. What about for the second pair? It's 4 years less. How do you say 4 years less as a number? -4. What about for the third pair? 3 years longer, so that's +3. And what about the last pair? 7 years longer, so +7. So what we've really got is the fact that the first pair gave us a 2, the second pair gave us a -4, the third pair gave us a 3, and the fourth pair gave us a 7. Right. Well, right. So Now again, what I want to emphasize is why are we allowed to take 81 minus 79? Because that was a pair. In our experimental design, we said that's the pair of whoever, 37-year-olds. Normally, when you have two groups of data, can you take one value minus another value? No, because they're not paired up. But here, we said we're going to pair them up. That's what match pair design means. So now we've got our differences. Now what can we do with these differences? Yeah, now we can take an average. Notice that we've taken two sets of data, but because they're in pairs, we can take differences. And once you've got differences, you've just got one set of numbers. And you know what you can do with this one set of numbers? Treat it like your data set. And now we can just do our analysis on these numbers. Okay, so the thing I want to go back and introduce the notation for all this business. Yes. Yeah. So the thing is, you now do your analysis on this just as if it were a regular sort of problem that you know how to deal with. So the only thing is I want to introduce you to the proper notation for this, because 2, -4, 3, 7, in a sense it is your data set, but in a sense it isn't your data set. What does it represent? What it actually represents are differences. So for that reason, we don't call these data values X, we call these data values D. D stands for differences. Okay. So that's really the only thing. Okay. So we represent data of differences with D. Okay. So now, here's where we go back to, now we need to make our claims, write our notation and all that. So in this case, remember, the claim was that BMW owners live longer. So what is that? That's a claim that says what about our difference? Right. Well, how would you write that? How would you write that in notation? So if BMW owners live longer, one way to say that is that the first one is bigger than the second one. But we don't want to talk. But if you say first one bigger than second one, that's really treating it as if it's two separate groups of data. We really want to talk about the difference. So if the first one is bigger than the second one, what happens when you take the first one minus the second one? You get the difference, and what should it be if BMW owners live longer? It should be a positive number. And the way that we say it in math, greater than 0. Right. So in words, you would say, well, your alternate claim is that the difference is greater than 0. But again, in notation, what is that? D is greater than 0. And then your HO is just D equals 0.
Why is it 0? Not 0.
Because what was the claim? The claim was that BMW owners live longer than Toyota. So that just means greater than. So if A, so just some simple algebra. If A is greater than B, what happens when you subtract B from both sides? You get A minus B greater than 0. Actually, let me... So, sorry? Okay. Well, notice that, so now we've just got the claim that D equals 0, D is greater than 0. Well, now we've got a set of data that represents D. So now we can just treat it like a regular set of data and go ahead, take the mean, take the standard deviation, blah, blah, blah. Just like we normally would. So, So what's the first thing we have to do? We have to calculate the mean. Okay. So the mean. Now what's the notation for the mean? Normally what's the notation for the mean? X bar, but guess what the notation is going to be here? It's D bar. Exactly. So D bar equals, add them up, divide by 4, you get 2. Next, what do we have to calculate? So the standard deviation, and that notation is still S. So how do you find the standard deviation? Yep. Okay. So we got 2, -4, 3, and 7. Then we say equals standard STDEV of this business, and yeah. Where's my? There we go. One more. And one more. Okay. So 4.4561. 5461. Okay. Now what else do we need to find? Exactly. And how do we get that? Yep. Take this, divide by the square root of n, which was 4. So that gives 2.2730. Here. Let me just fill in a reminder of what we're doing. S divided by the square root of n. Okay. Okay, and now what do we need? Yep. Okay, good. So let's draw it. So when we draw it, what do we write down here? Okay. So 0 in the middle for what? What distribution are we using here? Why does it have to be a T distribution? Because it's S, right? Notice that for this, there's no way to have sigma. We're never going to have sigma. It has to be S because we calculate this standard deviation from the sample, so we have to use the T distribution. Okay. So these are T-scores. Okay, and what else should we mark off? For D bar. Okay, so for D bar, what number goes in the middle? Nah. Remember, this is a hypothesis test. So what number goes in the middle? 0. Which 0? The 0 from the hypothesis. Does that ring a bell? Okay. So remember that we have HO, D equals 0, H1, D is greater than 0. So remember that we take this and we then say mu for d bar is 0 because it comes from our guess for the population.
So now it's a point of 2.
Yes, and so what are the value do we mark off?
2.
We mark off the 2, which is a d bar value. There you go. And then we do what?
Shade to the right.
Shade to the right. Remember hypothesis tests?
Line over.
Okay. Sorry?
No, it's the mean. It's the mean of those.
Where does that 2 come from?
The mean.
From the mean.
Right, the mean d bar. Comes from d bar. Okay. And so now what do we have to do? Now we have to find the t-score. And how do we do that?
2 minus 2 minus
Right, someone not named Oshrit, how do we do that? No, not statistics. Sorry? I don't know, did you? 2 minus 0 divided by what? No. Which standard deviation do you have to use? Right. Okay. Alright. Okay, so yeah, it's exactly what you just said. It's d bar minus mu for d bar divided by s for d bar. Right. Okay, it's been a while, I guess. Alright. So our d bar was 2, our mu for d bar from the hypothesis is 0, divided by 2.2730. Yep. And you work that out and you get 0.8799. And what do we do with that? Fill it in on the picture. That's the t-score. And now what do we do with that? Find the area using stat disk. Exactly. Okay. So, which distribution are we using? T distribution. And what do we fill in? And what's the degrees of freedom? 3. And then what? T value, which is this. Evaluate. And there you go. So to the left, okay, 0.7782, to the right, 0.2218. Yeah, I'm going to round it so they add up to 1. Okay. And so now what do we do? Right, which is? That D is greater than 0. Right. So we're 0.7782 confident that D is greater than 0. Now what does that mean in the context of this question? We're 0.7782 confident that BMW drivers live longer. Exactly. Sorry? I'm going to talk about that in a second. Okay. So is that straight? Okay. So, so one thing I did want to say, so I have this little note over here which has to do with what Benny asked before. Let me drop this note down. Okay. So Benny said, why is it 0? And it's because if you're saying, A, like as I did a little algebra there, if A is greater than B, then A minus B is greater than 0. Now, usually we're going to wind up with 0 as the guess, because usually you're saying one thing is bigger than another thing. But it doesn't have to be that way. So what's another way to state it so that you get something a little different? You could say at least 5 years longer. Or more than 5 years longer is a better way to say that. It's a note for myself. It's a note for myself. Okay, so Benny, does that make sense? So that in this case, more than 5 years longer is a way of saying that the difference is bigger than 5.
How would we know that before we actually do
No, it's in the question. So this question said, do BMW owners live longer than Toyota owners?
Right.
Well, how could we have asked that question differently? We could have said, do BMW owners live more than 5 years longer than Toyota owners? It depends how the question is asked.
Right. And then if the question was asked that way, then our hypothesis value would change from 5 to 0.
Right.
Oh.
Does that make sense?
Just understand it.
Okay. Okay. So that's how this sort of question goes. Okay. So let's see. All right. So any questions about that problem? All right. So why don't I give you guys a couple. Oh yeah.
So, if D is bigger than 5, I mean, according to the data, we'll have to do it all over again with the 5 in the middle.
Right.
But we'll have very little.
Well, not for this data, obviously,
Yeah.
right? Okay. So now I want you guys to work on this problem. Are men paid a higher salary for the same job than women? And here's your data. So first of all, notice how it says, are men paid a higher salary than women? So what are your claims? Yeah. Larger than, right. In particular, the difference larger than 0. Now, why in this problem, why are we allowed to talk about differences?
But it's a match pair. 25 years old.
Right.
It's
But
the same job.
right. Same job and what else? Looking at the data, what else is, what allows you to take differences?
They're male and female, right?
Okay, but I could just have a random group of males, and I could have a group of men and a group of women.
They're the same age.
They're the same age, right? And in terms of design, what does that mean? What is it? They're matched pairs, exactly. So they're matched pairs by age, so you can directly compare, for example, what number to what number.
37,000.
Right. So, for example, you can compare 37,000 to 35,500 directly. Now, and by the way, why does it make sense to do matched pairs using age for this question? Exactly.
What was that?
Age has a very distinct and typical impact on how much money you're making. Typically, we expect what? Older people have had more experience and they'll be making more money. So in this case, I didn't just match pair for just because I said so, but because there's a real reason to do match pairs by age. You would never compare the salary of a 60-year-old with a 30-year-old. Doesn't make any sense. At the same job. Okay. So here's your data. Go ahead. Now, I'm going to show you a little bit of a shortcut for getting through this. Okay. So, 37,000. Oh, alright. I don't need all those decimal places. Let me fix that. Okay, let's just do it like that. Okay, so for the man we got 37,000, 43,000, 44 here. Okay. Next. Okay, so here's so I've entered in the salaries for men, salaries for women. So let me show you how to do this using the spreadsheet. So what do we want? What we want is, actually let me insert a row here. So this is men, women, and what is it that we want to calculate? We want the difference. So let's make the spreadsheet do the work for us. What we want is the first cell minus the second cell. So you just type equals, click this, or type in C2 minus this one, and it does it for you. But now here's some spreadsheet magic. You click on the lower right corner and you drag it, and it does that calculation for you for every pair. Now you appreciate it. And so now what can you do? Next thing is just equals average of the differences, hit enter, and standard deviation, STDEV, of the differences. Hit enter. And there you go. Because the numbers are so big, I'm just doing the nearest integer. Okay. So why don't we use that and finish out the problem? So what did we find out? We found right. So using this easier way, what do we have? We have D bar equals 2600, and we have S equals 3537. Okay, so now what do we need? S for X bar. And how do we find that?
For people.
D- Quite so. Yes. Uh.
Oh yeah, you wrote 3.536.
And I'm rounding. So yeah.
35, 37, or
No. Okay. So we want 35, 37 divided by square root of 10. And that works out to what? 0.498. I'll just put 0.50. Okay. And so now what? Yeah, draw the picture. Now what are we drawing the picture of? Or I mean, what I mean is what distribution? Yeah. Okay, so how do we label this? Okay, so there's a T, and what else? And shade to the right of 2600. Yeah. Because these numbers are so big, I guess I'm being a little liberal. You shouldn't get something totally different. Oh, okay. If you want to use that, that's fine. Okay. And so now what do we need to do? Not stat this. Find the t-score. So t equals 690. And what does that work out to be? Let's check it. You get where's my okay. 2.3245. Okay. So we could fill that in on the picture. And now what do we find? Using stat disk. Okay. T distribution and degrees of freedom is 9 and our T value was 2.3245. And we get, there you go. There you go. And then 0.0226. There you go. D is greater than 0. Men get paid a higher salary than women for the same job. Exactly. I made this up. I made up this data, I should say.
But using this formula, would it be like more accurate than the usual?
Well, I mean, you could do this study. You could actually get data and do this study in the real world.
Oh.
Yeah. Okay. So, any questions about this? Okay. Yes. Right, if doing it by hand, you just add up the numbers and add up the differences, divide by 10. Yeah, sorry? Oh, well, I mean, so it depends if you interpret those as commas or decimals. So if you like, you could think of it as 2.6 thousand. Yeah. Also, you'll notice that sometimes people will say, "What was your?" Sometimes things like salary data will be recorded in thousands, which is actually how I sort of typed in this problem. So the salary is actually 37. The first salary, for example, is 37K. So you just type it in as 37, knowing you're working in thousands. So then 2.6 is 2.6 thousand, which is $2,600. Is that okay? Okay. It's regardless. You should get the same. At the end, you should get the same numbers. Same conclusions. Okay. So that is hypothesis testing for dealing with two samples using matched pairs.